Welcome everyone to today's Munich AI lecture. It's a pleasure to have Sebastian Scherer here from Carnegie Mellon University. He's a well-known researcher in the field of robotics and also computer vision for autonomous systems, for drones and also other types of robots. And we're really looking forward to his presentation here today. The floor is yours.
Thank you, Daniel, and thanks for giving me the opportunity to talk a little bit about what we're up to and how we're thinking about autonomy. So I actually want to start kind of at a very high level, and then we'll dig down into more of the details. And so, if you think about, we had elevators about 200 years ago, and we're still struggling with other autonomous systems today. And so, we're seeing that there's a lot of push to try and get these systems out. And as I'm sure you're familiar, we have this traditional sense, plan, act cycle, right? So, what's the difference between an elevator and let's say a drone or a robot that's self-driving or off-road driving? And so it's really there's kind of three main differences, right? For perception, for an elevator, and elevator is actually more complex than I'm making them here, but just to give the example, you have a limited sensing, has much lower noise, right? You know what state you're in, while for drones, the perception space, it's much larger for robots. In terms of thinking, you have larger action space. Instead of just discrete actions, you have an infinite set of actions, and when you execute something, you might not end up where you think you were going to be. So you're going from a discrete action space to an infinite action space. And so if you think on a very high level, one way people have tried to handle this is to try and remove uncertainty, right? So, and that happens in our everyday life. If you're driving on the road, if you're at an airport, you try to remove uncertainty by adding rules, by making right angles, by adding structure. But the kinds of problems that we're interested in is really where we are operating in these uncertain environments where you have lots of less structure, and you have to deal with that lack of structure. And so really trying to embrace this lack of structure, you have to think about, how do I handle this uncertainty? And so the way we do this is kind of at a couple of different levels. One is by having multimodal and redundant sensing, lots of filtering and fusion. And then on the execution side, to allow multiple futures and then minimize the assumptions on the system. And so next, I'd like to give you an example of how we looked at this for the SubT challenge, and then kind of how we are going beyond that right now to see how we want to further handle these harder situations. So one example to think back on, was a lot of you might remember this Thai cave rescue for the soccer team that was trapped. And so the way they actually navigated is by hand drawing maps of the caves and trying to figure out how to get there. And this lack of information was a real challenge. And so as part of the SubT challenge, we looked at how can we solve this problem, not only for caves, but also for other situations. And so it really kind of brought out a lot of challenging situations, right? So caves don't have any structure, right? You don't have level ground, you have slopes. There's lots of complex geometry sometimes. So you can see here there's lots of thin obstacles. And then you have to navigate in these tight spaces with a complex topology. And then also vertical motion, as well as degraded sensing. So here we're flying, for example, inside a mine where we're kicking up some dust. And so this was all kind of motivated by the DARPA SubT challenge, where there are 3 different types of environments we had to look at. And so let me kind of show you a little bit, how we did this in this sense in a more traditional way, but also kind of showing you what it would take to think about how do we incorporate learning, how do we improve the performance of these things without kind of throwing away everything and saying, okay, we'll just go from image to action. So it actually starts, so one of the challenges actually starts with the problem formulation. So the problem is actually not just an exploration problem where you're trying to say, okay, maximize information gain of the area or something like this. You actually have two objectives. One is you're trying to maximize the map you see. At the same time, you're also trying to maximize the coverage that the camera has on the map. So for example, to detect objects, we typically use a camera a lot, and the camera has to look at something to be able to see it, right? So it doesn't just help you to create a map of that area. But our LiDAR scanner can see much further, so it can create a map, 100 meters out, but the camera can really only reliably detect objects maybe 10 meters away. So the way the system is decomposed is in these 5 components. So one's kind of mapping part. There is the behavior executive that really tries to ensure that the system always has something to do and behaves correctly. A global local planner and the controller. And actually the behavior executive is quite important because in this setup, you don't have a human operator really that has a mental capacity to do anything, because they're running a team of about 10 robots, and they cannot, control an individual drone and give inputs. So everything has to be fully automatic, and this behavior tree decomposition was quite useful to give it robustness. One other thing to note here is you can see in the exploration tree there's actually many different behaviors, and one of the things that turned out to be quite useful is to have different behaviors if different algorithms fail, right? All of these algorithms have some shortcoming. And so, there's one fallback algorithm that's in there. For example, that's the equivalent of go in a random direction, right? Because anytime we're just hovering, we are not gaining more information, right? We're just burning energy. And then another big part of it is how do you get back to return your data that you've been gathering to the base station, because you might be out of communication when you're actually doing the exploration, because in these caves and mines, you don't have good communication. So the maps that we create, there's a couple different types of maps. There's an exploration map, a navigation map, and a local planner map. And this, so let me first tell you about the global maps. So we have, we want to create these frontiers for the system to go towards. And what you see in this visualization, and you'll see that a couple times, is this green map is what we have seen with the camera, and this gray map is the LiDAR point cloud map. So you can see that we see a much wider area with our laser scanner and a smaller area with the camera. And so here what we're showing is that when you're trying to, a typical way to construct these search points is to look at the surfaces and the edge between unknown and known, and that's actually not so effective, especially if you have things like dust and so on. So what we're actually doing here is subtracting the map of what we've seen with the camera from the LiDAR map to get our next goal points. What you get from that, this subtraction, is actually the points you want to look at. So what you then need to do is figure out which direction do you want to see something. And so we are sampling a viewpoint, different viewpoints, to try and figure out what direction to look at it, and then cluster these viewpoints to have a set of goals for the planning algorithm. And then we have a set of different planners actually running that can run depending on which ones are successful, and they have some hand tunes objective function that they go for exploring the space. We can run multiple drones at the same time, and the way they coordinate between each other is using shared exploration maps. So there are two types of maps that they share. One is a volumetric map of what another drone has already seen, and the second one is a road map, and that road map can be used to navigate quickly to an area if the area that's around the robot has already been seen many times. And so here you can see an example of some of these shared maps. So we have this grid map here that tells us what has been seen by another robot. And then here you can see an example of this road map that's shared between different robots. It's also shared with the ground robots that are exploring. And so we can put all this together then. Yeah, on the left you see what UAV1 sees, on the right you see what UAV2 sees, right? So it sees these red maps tell it don't go in that space because another robot has already seen that. And so in the end we get these goals, and then these goals go to a local planner. And there's other things that happen here is one of the big factors is speed control, because it can be very narrow spaces and also large spaces. And then you also want to have to kind of turn to fit through narrow spaces like doors. And so let me just kind of give you a quick sample of how this looks like. And I know I'm going pretty quickly, but I want to kind of give you just a taste of what this type of system looks like. So you can see here the system first looks in the bottom of that subway station, then knows that it hasn't seen the top, so now it looks at the top, and you can also see it kind of turning to turn the camera to look at different spaces. This is during the final runs for the SubT challenge. Here you can see it kind of going through a door. And so all of this is fully autonomous. You can also see here the robot moves quite a bit faster if the space is more open. And actually in this type of mines environment, you really don't ever want to hover, because as soon as you start hovering, you kick up dust and then you're done. So you can also see that here inside a cavern. And part of the challenge that we have to deal with here is as well dust filtering. So we have to filter out dust, but we also, in this example, you can see there's quite thin obstacles. So you can see these kinds of posts hanging down, and then the system has to still be able to handle this. So all of this is fully autonomous. This example here was actually an accidental experiment. We wanted it to go down here, but then it found that opening and started exploring, so we just let it run. But you can see some of these challenges that the system has to deal with. And then also the camera field of view is a bit larger. Here you can see kind of going down a staircase. And you can also see some of the planning going on. This magenta point is the goal point that it has. And so these are some of the results. So, yes?
What sensors does this system have? Is it camera, LiDAR,
So it has, I didn't mention, so it has a LiDAR on top, fisheye forward camera, mainly for object detection, and then it has a top and bottom real sense depth camera to be able to go vertically. For the depth camera, it's like 3-4 meters. For the LiDAR, it's about 80 meters. Yeah. And so, one of the challenges here is also that the environments can vary in scale quite a bit. So you can be from narrow corridors to a wide open kind of cavernous cave that's, tens of meters wide. Actually, this is maybe a good point for any other quick questions on this. Yes. The LiDAR. I'll talk a little bit about the localization later. Yes. Yes. So the way the synchronization works, there is in the challenge was what's called a DARPA frame. Basically, at the start of the competition area, there's some surveyed points, and we basically measure in the robots with total station for the first robot, and then for subsequent robots, they align themselves with the map of the first robot. So when they start out, they're basically aligned. There's a certain special procedure for, there's also drones that take off from the back of ground robots, and so they align to the map of the ground robot. And so there's like a whole procedure for that takeoff. So there are some lessons that we learned, and I kind of want to go back out a little bit again to talk about some of the things that we've been doing since. And so one of them is to try to avoid overfitting, right? You can see there's a really large range of environments, and it's pretty easy to make the system work very well in one type of environment, but we don't know what we'll get in the competition. So we actually have to try and find a set of parameters for these things that works in a wide range of situations. And one of the challenges here also was just fitting all the computation on board, right? So we could have run fancier algorithms, but we had to do object detection on board, planning, control, everything had to be on board. So SLAM. The actual problem is a multi-objective problem. It's not just explore as much as you can, and we're really trying to get some resilience by having redundancy in a couple different ways. So there's, of course, multiple drones, but then also multiple algorithms running. There's multiple sensors for the SLAM. And here you can actually see a nice case of recovery. So here the drone went into a tunnel. DARPA had set out some smoke bombs that really affected LiDAR. And so the drone detects that it can't go any further and then backtracks, but the SLAM had drifted a little bit, so it hit that sign, but then was able to recover and just keep on exploring. Now, I want to kind of come back out a little bit, and so one of the challenges we had and kind of that's been driving is, so on the right here what you see is kind of our objective function. Right, and so that drives what points do we pick, and it's this whole hand-tuned function with magic numbers, right? That with a grad student in the loop, right? Grad student descent essentially comes up with the optimal score to pick, right? And so that's really, and we arrived at some local optimum that traded off performance in one versus all environments, but it's really tough to actually tune that, right? If you talk to the operator, they'll be like, oh, don't go over here because I know probably there aren't as many objects that I want to find over here. Go more over there. Don't go in Windows. Go over to this place, right? So it's actually really hard to capture this in a function, right? And it's always very desirable to say, hey, we find the optimum, solution that maximizes information gain, but nobody cares, right? Like, what you care about is that the system behaves in a way that that is desirable. So that's, yes.
Another question: with all the sensors you have on board, the LiDAR, the depth sensing cameras, the molecular camera, for 3D perception and localization and path planning, it predominantly relies on the LiDAR.
Yes. Yeah. So it's mainly so for and this was primarily for computation reasons. For the challenge we mainly used the LiDAR.
And once it kicks up dust, that affects the LiDAR.
Right. Yes. Actually, it affects the LiDAR probably more than the cameras, because you're sending out a laser beam and then you're getting a straight reflection back from the dust, while typical visual sensors will triangulate, right? So you're actually triangulating past the dust. So even if you have like active illumination and you're triangulating, it's actually better in dust. So we actually had to do quite a few tricks for the dust. So there's one of them is on a local mapping side. We have a dust filter that removes dust and then actively adds thin objects that are linear back in. So we actively detect things like wires and other things that are hanging down because you'd lose those otherwise. And then for SLAM, a big trick was to essentially detect if you're in dust and try to increase the distance where you're looking for features, because what happens is when you're in dust, you get lots of these little features inside that dust cloud that look very attractive to the SLAM algorithms because they're dense together and so on. And so we actively increase the minimum distance when we're inside dust, because typically there's a certain ring around you where that dust shows up. So kind of coming back to the goal, right? So when we think about the this kind of hand-tuned function, it's not very desirable. So we can try to get machine learning into this to help us with this in a couple of different ways. So one is to try to map sensor output directly to certain inputs that we want, and we can potentially improve the filtering. For behavior, imitation learning can be quite useful. And then also on the action side, right, we don't necessarily know what the executed action is. So can we learn that? And so in the lab, we've been kind of trying to go down kind of three thrusts to overcome this. So one is to try and actually, because we do a lot of field robotics, to come up with these problems and provide challenge data sets and simulators and so on that are useful for these problems. And then you'll get some good perception outputs and then see how we can use those for effective decision making. So let me show you a little bit about these data sets. So we have released two data sets. One is a very large simulated data set called Tartanea, and then also a real-world data set that's a combination of data from the SubT challenge plus some other local data that we've collected with many different types of degradation and challenges. And the idea is that the simulated data set can really help you if you want to do something learning-based, because there's zero noise, right? You can eliminate all noise. So if you're, for example, trying to learn a transform or something like this, it can be very helpful. And then and still add degradation and so on. And then for the SubT MRS, it's really helpful because it's realistic data, again, with ground truth, where we've taken survey scans of an environment and registered this to real-world conditions. There's some other data set, for example, the Tartan Drive data set that's more for off-road driving. So you can it's a lot of driving in very diverse terrain, on trail as well as off trail, with lots of proprioception data. There's also the Tartan Aviation data set, so that's more for visual detection of aircraft, but it's similar. Also, you get air traffic information as well as speech information. And then most recently, we just released a data set that's 1 year's worth of air traffic in the US with some nice Python APIs, as well as a trajectory prediction model that's trained on this data. And it covers about 48 airports, has maps on it. That might be useful for some of you. So we use these data sets, to really try and move things beyond, these simple data sets that are out there, that are not really suitable and were not initially designed often for learning-based systems, right? I mean, if you think about something like Kitty or so, it has been great, but it's not, it does not generalize to anything learning, right? Like you don't want to ever just show something on Kitty. So I think that, there were some questions about the SLAM. So what we ran in the challenge is an algorithm called superodometry. We've been working on this since. So this is a multimodal version of superodometry that includes visual and thermal data. So here, for example, we're going inside a smoke room, so the LiDAR and the visual will not work at all. And then here it's only relying on the thermal cameras to do visual odometry. And then when it gets back out, it switches back to the LiDAR. Then it actually gets to some corridor that's very thin and long, where the LiDAR does not have enough features, so it transitions over to the visual odometry. And so the trick here is, how do you actually get a good uncertainty to be able to do this trade-off, reliably, right? I mean, it's so that's kind of one of the big challenges here. And so we look at the structure of the features to tell us which directions are constrained, and you can see that in the lower level here, these 6 numbers tell you how well the LiDAR odometry is constrained, and that's really the driving force, because we often LiDAR odometry is most accurate for us. Some things that we've been looking at as well more recently is Gaussian splatting for SLAM. There's an algorithm called SPLATAM, and this is still, I would say, not as reliable as the superodometry type algorithm, but has the potential to give you much denser mapping, and has the potential also to do some interesting filtering to allow you to be robust. So that's something we're kind of looking at in the future. And then we've also looked at place recognition using some of these foundation models to try and relax some of these constraints that we had, for example, for this initial alignment, instead using this place recognition to allow us to detect places. So there's an algorithm called AnyLog that we've developed. And then kind of the third thing is, on the perception side, we rely pretty heavily on LiDAR right now. And so the goal has been, can we do some depth perception using free fisheye cameras that are upward looking to try and detect, to extract depth maps. So what you see on the right here is actually a panoramic image that's stitched together from 3 upward-looking fisheye cameras. The image is renormalized on every frame, so that's why it's kind of flickering in depth. And so actually can run in real time on a Xavier NX. And it's been trained only on synthetic data. So we collected a large set of synthetic data using kind of our tartan air type of setup to create these fisheye images, and then to use these for depth mapping. And then the third thing has been to try and push going into smoke and getting better depth maps there. So I've been looking at using stereo images for depth mapping. And so stereo image is actually a little challenging, both for odometry as well as depth mapping, because they have very unique noise profiles, as well as the dynamic range of the images is typically 16 bits, so you have to choose the right range of pixels you'd want to get out. So once we have this this kind of perception inputs, how can we improve how we make decisions? So one of the ways we've looked at trying to extend beyond this traditional frontier exploration that we did in the SubT challenge is try to learn what our expected payoff is, right? So because we have all the data from the SubT challenge, we can actually essentially forward simulate or look in the back, right? So you can say, okay, if you're at this point, what would have been the payoff if we had taken this decision? And so we can use that to learn a reward function, and that can really help you with exploration. I don't know if this is the most convincing example, but we can explore better if you look at the paper. And so now we'll kind of switch gears a little bit. So for, I've showed you a lot of flying things, but we've also been working a lot on off-road driving. And there's and one of the big philosophies we have there is that you cannot really label data well, right? So for off-road driving, if you're also off-trail, right, if you label a rock, there's big rock, small rock, it's really hard to label these things in a good way. So we've been looking at how can we predict roughness using onboard sensing or imitation learning or trying to explore. So this was one paper where we used the IMU data to basically look at how much acceleration do we experience, and that tells us how rough the terrain is, and then we can use that information to then pick different speed maps. So here we have this area, and then we learn different speed maps for different cost maps for different speeds, and then you can see here that it is able to pick up the cost of the different trail. So it doesn't say you can't drive into the grass, but at high speeds it's pretty expensive to drive into the grass. And the input here is a stereo depth map from a learning-based stereo that we developed called Tartan VO. Additionally, you can also, one of the problems we have is that we have pretty dense information of the LiDAR close in, but as we look at further ranges, the data is not dense enough. So what we're doing is we are doing self-supervised learning based on the close-in information to extrapolate the maps to the long range on the fly. So it's basically learning on the fly to extrapolate this information. So you can see here, this is the type of LiDAR input that we have, so it's pretty sparse, and then we can adapt this information on the fly to then build a denser long-range prediction that we can use for better decision making. And then lastly, when we actually execute the commands, there's a lot of uncertainty, right? Like, we can try to identify a model, but that model, with slopes and gravel and grass and so on is going to be uncertain. So what we've been looking at is looking at some ideas for physics-informed neural networks to try and learn a prediction model. So this is and there's a couple different ways you can do this. You can try to predict a delta, you can try to predict the whole thing. And the red line here you can see is our typical model that we have, that we kind of hand-tune to be as good as possible. And it does have an error, and actually when we run it on the robot, it also is more successful. So once we have all these inputs, now we want to we have these raw kind of cost-like estimates. So now we want to know how should we drive, right? Should we go left? Should we go right? And so what we do there is inverse reinforcement learning, and essentially use this data set that we collected to try and match the frequencies of where a human drove with what we predict. And so then we can put all that together and then guide the robot. Maybe this is a good point for a quick pause on, are there any questions about the off-road driving real thing? Yes? Mm-hmm.
Let's say label them as high cost, but I mean it's not too easy, for example, off-road.
Right. So yes. So this is kind of the problem that a lot of the self-driving world has looked at, and we have stayed away from self-driving. But for the SubT challenge, one of the things we did have to deal with is you have narrow corridors, and you might just meet each other, right? And so now what do you do? And what if the corridor is too tight that you can't get past each other, right? So now you have to come up with some kind of parking routine because your drone might run out of battery, and so there's a whole avoidance, local avoidance that also considers the speed to try and avoid this. But yeah, for the off-road driving part, we have not looked at dynamic obstacles. So kind of the last thing before I wrap up is some work that uses this data set I talked about earlier to do intent prediction, right? And as some of you might remember this case in Haneda recently, right, where another plane landed on top of another plane. Here's one example that we had actually simulated and then tested using our policy that actually happened in real life a month later. And so this runway incursion is actually a big issue. So you can see here there's a plane that's holding short of this runway, and then there's another plane that's taking off. And so now that plane that's waiting is supposed to stop, right? But now he's going to start moving at some point. And then now the plane starts moving, and so we can actually detect that it happens before we're crossing the hold short line and that a bad event is happening, right? And so this whole game here is how early can we alert without having too many false alarms, and basically trying to push out that prediction horizon as far as possible. And so a lot of this is about mapping the speed maps, right? Like how fast what is the distribution of speeds that somebody is going to go at, because the types of decisions are pretty fixed, right? I mean, there's usually 2 or 3 junctions, and the real key thing are hold short lines. So kind of giving you some of the updates of what we've been up to in terms of our most recent research, maybe trying to come back out a little bit. What is wrong with the current state of the art, right? There's great success in various subtasks. There's some of these end-to-end action models, but I've not seen them very successful. And the tasks that they can do are limited, and they're unable to abstract. And so I think one of the high-level things is that this feed-forward type of system is not enough, right? Most of the systems you look at right now that try to do RL or something like this, you're going feed forward, right? You have some input, you're mapping to an output. And that's great to learn a compression of your actions, but it's not, and you get lots of the leverage, lots of leverage with learning frameworks, but you have a limited ability to reason and abstract, right? And that's really the piece that's missing. And so one of the things we've been thinking about is how do you take these types of good things you can get with deep learning right now, which is these kind of open world perception models. You can actually get some sense of symbols, but then maintain the ability to abstract and reason. And so there is an area in learning called Neuro-symbolic AI, but a lot of these, there's interesting methods there, but they've really been focusing on very toy tasks that are not really robotics kind of relevant right away. So like NIST digits or some very simple benchmarks that have very specifically instantiated symbols. So we sat down and really tried to push for a benchmark that's a little more relevant to robotics. And so we call that Logicity. And so the way that works is that we have abstract first order rules. So we have some concepts, rules, and then we have instantiations of a set of agents. And then we have a simulation that takes these inputs, use an SMT solver to try and figure out what the next tasks are, and then goes to the next state. And then we also have a rendering engine that uses diffusion models to try and to be able to generate a large set of different appearance-looking simulation. So if you want to have perception models, you have some way of generalizing and showing generalizability. And so the nice thing here is that we know the ground truth rules and concepts, right? So it's not just some hidden Atari game or something where we don't know all the rules and can't write them down, you can't change them, and you can't have abstractions, right? Here you can have an abstraction and you can transfer it to another world, and ideally your algorithm should generalize, right? And so based on this, we define two kind of benchmark tasks. One is the sequential decision-making task where you really have to reason over a long horizon. So you want to go from one start to a goal, and you have to reason, hey, should I stop, go faster, slower, and so on. And there's different rules in here, things like stop signs, ambulances, pedestrians. So you have to be able to discover these rules, right? These rules are not known to you. And then another task is this abstract visual reasoning task, where you're given an image as an input, as well as a set of groundings for the agents, but you don't know what rules those agents necessarily have, and you're trying to predict what is the best next action for each of the agents. And so this is just kind of a start that we are on to try and really push some of these methods more towards a robotics relevant application. And so we hope that having these abstractions will allow us to get to a sense where we have these learning systems that can also reason, where you can still use RL to compress this into a policy that's faster, right? You can always do that, but it gives you a way to generalize and also maybe handle things like catastrophic forgetting. So just to kind of summarize, the complexity of the environment that we look at drives a lot of kind of our research goals. You have to think about uncertainty in sensing to make good decisions, and the choices of actions also drive the complexity of the problem, right? So if you're trying to go from an elevator more to something that's flying in the wild with a lot of uncertainty, there's a lot of things that need to happen to be able to do that successfully. And so if you look at a lot of current learning paradigms, they're very brittle to domain shift and adversarial attacks, right? So you can think about just shifting the brightness of an image, you might not actually detect an object anymore, right? It's very easy ways to mess up object detectors, just as an example. And this feed-forward inference of network architectures is not sufficient for this intelligent decision-making, right? If you think back to the first beginning, right, where we have this kind of hand-engineered, quite complex system, right? Even if you want to learn this from end to end, you still need to have this type of behavior in there, right? And one of the areas we're looking at is trying to combine this symbolic reasoning with neural approaches to create these good abstractions that hopefully generalize with less data, since in robotics, your data is much more limited than in a pure computer vision sense. And there's still a lot of work to do in terms of learning from experience, learning continuously, all these things. Okay, thanks. Thanks, everybody.